Good evening, everyone. Today we'll be looking at post-hoc procedure, post-hoc test. We have been discussing analysis of variance for the past maybe 1 month or 3 weeks. And the first thing we look at the understanding ANOVA, then we talk about F distribution. Then the last lecture, Tuesday, we look at plan comparison or plan contrast. So, and today we'll be looking at post-hoc procedure, post-hoc test. And I have said that plan comparison and post-hoc tests are two different things. The method you employ or you deploy, whenever you carry out analysis of variance, and you can find significant difference. If you know in analysis of variance, you are comparing mean of more than 2 groups. So 3 groups, 4 groups, 5, it can be any group, then 3 and more or more. So you know that if you are to pair them, there are different ways you can combine those groups. We have already established the fact for 3 groups, you pair them in 3 ways. For 4 groups, you pair them in 6 ways. For 5 groups, you pair them in 10 ways. Like that. Now, if you didn't find any difference, you can be sure that there's no difference anywhere. You rest your case. That will be the end of analysis. But in a situation where you find a difference, you want to know where the difference lies. Since for the 3 group now, you are comparing 3 means, and you find a difference. There are 3 pairs. There are 3 different ways you can combine them 2, 2, 2. Where does the different lie? That's what we want to look at. So in trying to do that, you can either use plan comparison, which you have discussed in the last lecture, or you use post-hoc procedure, post-hoc test. So what are these post-hoc tests? These are the pairwise comparison. When you say pairwise, you pair groups. So let me mute everyone because some people are making noise. Because let me just mute everyone. Okay, I'm trying to look at. Okay, okay. Everybody is muted. Let everybody be muted so that it doesn't disturb the. So these are pairwise comparison that are designed to compare all different combinations of the group, all different combinations. If you pair them, so for 3 groups now, you have 3 different combinations. For 4 groups, you have 6 different combinations. For 5 groups, you have 10 different combinations. They are used when you are interested in exploring that data for any between group differences, between means that exist. That you want to see that the difference exists somewhere. Where does it exist? For example, when you are having 2 groups now, 3 groups, that is 3 groups, and there are 3 combinations, you can 3 different ways you can pair them. For example, now the example of we are using the example of libido, the libido data, where you have the group that you receive placebo, the group that receive low dose Viagra, the group that receive high dose Viagra. There are 3 groups. Let's say they are A, B, C. So A and B, that is low dose and placebo and low dose. That's one combination. A and C, placebo and high dose. That is the second combination. Then B and C, low dose and high dose. That is the third combination. Where does the different lies? We're going to look at it. Pairwise comparison control the family-wise error by correcting the level of significance for each test so that the overall type 1 error rate across all comparison remains 0.05. What we mean here, you remember one of the reasons or the major, even the reason you don't compare, you don't use t-tests to compare more than 3 groups is that you end up doing many tests. And when you do many tests, your family-wise error increases. That is, if you say you rejecting no hypothesis as 0.05, But if you carry out 3 tests, you're actually rejecting as a level in 40.5, 40.3%. That is 0.143. Something that you are thinking is 5% before, it has turned to 14%. And when you do more, the error rate increases. So what better in this case now, you are still preparing them to compare them 2 by 2, 2 by 2, but they've adjusted so that you will not have that family-wise error. Even though at the 0.05, the adjustment is being made, which you cannot find in direct t-test. So there are several ways in which family-wise errors can be controlled. The most popular and easiest way is to divide by alpha, by the number of comparisons, so that cumulative type 1 error is below 0.05. The method is known as Bonferroni correction. So SPSS and many other software, they have some correction, but SPSS has 80 post-hoc procedures. So those are the one I want to show you, those different procedures. Look at them. They are 18. You see the first set are 14, the second set are 4, making 18. And in the first set, when you assume equal variance, you know, we talk about this issue of equal variance or homogeneity of variance. When you are comparing groups, rather means of group, like even t-test, ANOVA. Apart from the fact that for you to use t-test or ANOVA, which are parametric tests, for you to use that, you require that the data set follow normal distribution. That's the first assumption. That is data set follow normal distribution. So for you to say, oh, it is normally distributed, you can use parametric test. That is the most important and the number one requirement or assumption. The second most important is homogeneity of variance. Even though the means for the different groups are different, of course, that's why you are comparing they're actually different or not. The variance, the standard deviation, the variance, the standard error, call it. You know, when we talk about, sorry, I was out, I don't know, the network knocked me out, I don't know how to do to improve the, once it's evening like this, I don't know the network, and it never has been stable all this while, but once it's evening, maybe we have to be doing our work earlier. Now, what I was discussing before, so the requirement, the first requirement is that the variable must follow normal distribution. The second one is homogeneity of variance, that is equal variances between all the group must have the same variance. It doesn't mean that they will be the same, but if you put it to test, there should not be any significant difference in the variances. That's the second requirement, and the second most important requirement. Or in fact, those are the two important requirements. The other two requirements, they are not as important as these first two. The other two requirements is that it must be on at least interval scale. That is, it must be something that has number, must be quantitative variable. You know, but there are some situations that you use ordinary variable. Naturally, they don't have number, you just assign number to them. You can still use them sometimes, but it's part of the requirement that it must be on interval scale. That is a quantitative variable. And the last one is that it must be independent. But that one can be violated. So you can see the last two may be violated, but these first two, normal distribution and homogeneity of variance, equal variance, they are very, very important. So that is why here now, you see the correction, two set of correction post-hoc tests here. We have the one that assume that there is equal variance, that is, there is homogeneity of variance. The other set, those ones that contain 4, they don't assume. In a situation where you cannot assume, there are no equal variance. Though even that thing may follow normal distribution, there's no equal variance. So the first set that assume equal variance, there are 14 number you can even see in SPSS. Though actually is different people that design this correction, different intelligent people, statisticians that invented the correction. Of course, the people that developed the software now incorporate them into their software in case the one you want, anyone you want to reuse. The commonest one you might have heard of is Bonferroni correction. What it does is to divide the number of the tests you are doing by the alpha so that it adjusts. But it has been criticized that it's overcorrect. Bonferroni overcorrect. So people have already, so sometimes something that will have been significant because it has overcorrected it, it will not be significant. So just by dividing, if I did the test now, so I will now divide 0.05, which is my level of significance. If I did 3 tests, like we have 3 groups now, you now divide the 0.05 by 3. So there's overcorrection. That's the criticism. We have what we call least significant difference, or LSD. You will discover that is the best. Well, can I say the best? That's the one people use. It allows, if there's correction, it's very sensitive. That one, this number 2 is very sensitive. So that's why you see many people using it. So there was when we were having one of the training in Port Harcourt, and one lady, a PhD student, said that yes, no wonder when she did her work and she used Bonferroni, they didn't find any difference. And the supervisor said, go and use LSD. And by the time they use LSD, they could find a difference. Because Bonferroni has been criticized to have overcorrected. The LSD is better somehow in that sense. We have CEDAR, we have Sheffield, we have many of them, and they are there in the software. If the options are there, just for you to put the option. And those ones that you call variance not assume, we have 4 of them. We have Donne, Tamhin, Games-Howell, Procedure, and Donne. Now, this is Hoc Bonferroni. Now, I want you to see the how to after running it, because I don't usually run it here in the lecture, but in our workshop, we usually run it. And we have many of our workshops also that the videos are there on our site. Says after running that, like this, the libido data we have been using. This when you run it, you run the post. So you know we have run it. We discovered that where the significant that is with ANOVA, the F is 5.119 and the p-value is 0.025, which is significant. So we want to know where did this significant lie. We now use this method. The method, okay, this is Bonferroni. We use Bonferroni. Sorry, I'm back again. So we use Bonferroni, and this is the result we have. If you have use LSD also, you may get something better. The same thing similar. So look at the screen. You will see that what it does is that, you know, there are 3 groups. What it does is to pair the 3 groups A and B. And you know we have 3 groups: placebo, low dose, and high dose. You know, there will be repetition because this is programming and the computer is not human being. It's garbage in, garbage out. So what you see here, now look at the first one here. Let me use my annotation, the spotlight. You see, placebo here, you compare, this line compare placebo with low dose. This line compare placebo and high dose. For this one, low dose, you put it as the first one, compare low dose and placebo, compare low dose and high dose. The last one, high dose, compare high dose and placebo, compare high dose and low dose. So there will be repetition. Because that's the way you can do it on this program, because the computer is not human being to say, no, you have read. So if you look, placebo, low dose is the same thing as low dose and placebo. So when you look at it, you will now see 6, 1, 2, 3, 4, 5, 6, but it's actually 3, because you now see the one that is mirror image of the other one. Look at this one now. Look at the difference here. The difference between the two. The difference you are seeing now is the difference between their mean. You remember, the placebo group, the mean for the group is 2.2. For the low dose is 3.2. For the high dose is 5. So if you look at placebo and low dose, 2.2 minus 3.2. If you remember, placebo is 2.2, low dose is 3.2. So when you say 2.2 minus 3.2, it gives you -1. When you come here now, low dose and placebo is 1. It's the same thing. You now say, okay, 3.2 minus 2.2 is 1. It's still the same thing. It's only that this one is the opposite. If you remove bigger from the smaller, it give you negative. You remove smaller from the bigger, it give you positive. It's still the same thing. So when you come here now, look at this one, like placebo and high dose. You know the mean for the high dose is 5. For the placebo is 2.2. The difference will be 2.8. So you look at it now, placebo minus 2.2 minus 2.5 is going to be minus 2.8. When you come here where you say placebo and low dose, high dose and placebo, can you see? It's the same 2.8. Why this one is minus 2.8, this is 2.8. It's the same thing. So the same thing if you look at low dose and high dose. Low dose and high dose, can you see? The low dose is 3.2. The high dose is 5. The difference between 3.2 and 5 is minus 1.8. So when you now come to high dose and low dose, it's the same to 1.8. So you see that two of them are the same. One carry the different carry minus, one will carry plus. So when you now come to their standard error, it's the same thing. When you come to the p-value, you will see that it's the same thing. The difference between placebo and low dose is 0.845. That is, there's no significant difference. The same thing, low dose and placebo, 0.845. But when you now look for placebo and high dose, or high dose and placebo, you see the p-value is 0.025. That is significant. And if you look at for the low dose and high dose, is 0.196. It's not significant also. So the only what this result is telling us is that the only significant where the difference lies in the three group is between high dose and placebo. So the people that didn't take anything and the people that took the high dose, so the difference in their libido is significant. There's a significant difference in the libido between the two groups, these two groups. So, but between placebo and low dose, so there's no much difference. That is, somebody that didn't take anything and someone that just take the low dose of that drug, there won't be difference in their performance. The same thing, what is telling us, for somebody that take high dose and someone that take low dose, there's no more difference. So the issue now is that if somebody wants to take it, just take the high dose. That's what makes difference. So comparing the high dose and the person, either you take it or you take it very well. And that is what the result is saying. So the difference we have found in our ANOVA now is between the placebo and low dose. The other one is not statistically significant. If you lose least square difference, this other one is almost significant. This other one, this low dose and is it low dose? Yes. The difference between the high dose and low dose is almost significant because we have already said that for Bonferroni is overcorrect, while that one is a little bit loose. And when you now come, this one gives the 95% confidence interval of the difference you are seeing. No, the difference you are seeing is given the 95% confidence interval of what you are seeing here. Now let's just look at if you have your question, you can just write it. Now, okay, I think this table now show, yes, I think it's okay. Yeah, thank you. You can see now, this table is showing the correction by Bonferroni LSD, least significant difference method, Bonferroni method, and Games-Howell. And if you remember that Games-Howell is one of the example for when equal variance not assumed. Let me go back there. You see? Okay, Games-Howell. Yes, I see. So LSD and Bonferroni, the example you use when equal variance assumed. But Games-Howell is one of the examples when equal variance not assumed. So I just compare the three. Look at the three. If you look, you see the same thing if you look at it. You remember this one give you here Bonferroni. Okay, this look at Bonferroni, where it said the p-value 0 between low dose, high dose, and placebo, low dose and high dose, 0.025. This one is 0.008. Can you say LSD is more loose, is more significant? Look at where you say for between placebo and low dose, which is 0.845 for Bonferroni, is 0.282. Even though it's not significant, but the p-value is getting smaller. No, the smaller the p-value, the better the difference. So if you now look at the difference between the high dose and placebo, no, high dose and low dose, which was 0.196 with Bonferroni, what do you have? Is 0.065, almost significant with LSD. So you see Games-Howell actually lies, that one lies in between the two. So it's not as, it's still Games-Howell, does it lie between the two? No, it's not actually lie between the two. Well, if you look at it, well, if you look at the other one that was given us 0.025, is given us 0.023, 0.039. So you know here, equal variance not assumed. So some things have changed. But what I want us to focus on is look at Bonferroni and LSD. You see, sometimes it may make sense for you to use LSD rather than using Bonferroni. And so the interpretation is like as if you have come back to do the t-test you didn't want to do. Because initially you didn't want to do too many tests at the same time. You don't want to go and, since you're having 3 groups, you don't want to go and perform 3 t-tests. If you're having 4 groups, you don't want to go and perform 6 t-tests. But if it's 4 groups we're having now, and you find a difference, by the time we run our post-hoc test, it will give us like 6 pairs. It will give 6 pairs. And we need to search where does the difference lie. So the only difference between this one and the t-test is that for t-test, the family-wide error is there. But here, they have already adjusted for the formula in such a way that you will not make that family-wide error. That is just the difference. So don't say, we will have done the t-test. No, you cannot do t-test for when you are dealing with 2 groups or 3 groups or 4 groups. You do your, after all, if you do your ANOVA, and the ANOVA, there's no significant difference. You rest your case. You don't need to do any post-hoc test. Just move ahead. But it is when it's different somewhere, even you looking at the data, you will know. Whenever there's a difference, you will see the difference in their mean. You will know which one have higher mean, which one has the lowest mean. If there's going to be anything different, it's going to be much different to be in between this one that have the highest and the one that have the lowest. But of course, what we have to say, even though the other pair between the one that have the lowest and the one that have the medium, that's different you are seeing, that may still be significant if you put it to test. That is why sometimes it may not be significant. So that if there's a significant with ANOVA, there must be at least in one, this may lie between a pair, at least one pair. It may be more than one. It may be even between all the pairs for the group that is different line. And that is why you need to carry out either the plan comparison or so. Then you see that it is easier to understand the post-hoc and to interpret that, to carry out plan comparison. So normally people don't usually carry out the plan comparison. It's the post-hoc test that people carry out. Now, just to create a mental picture of what we have just done. Now, the same data set for that libido is put in graph like this. The green dot you see, they are the placebo. The green circle, placebo. The triangle will look like, I don't know which color, blue or whatever, it's low dose. And with the one, okay, the triangle is like purple, while the square which is like pink, is high dose. So if you plot the libido on the vertical axis, the participant, those people involved on the horizontal, you will see The dot now showing the value of each person. This first person have 3, this one have 2 point something. This, we're talking of you. This one has 1. This one has different. So if you now look at the mean, you see the low dose, the libidos, this group 1 that are in green, you see that averagely their own is lower. Most of them they are lower in value. While the low dose are medium in value, and as you move up, the libido is higher with all those high dose. But you see the horizontal line for each of them is the mean. If you remember, the mean for the load for the placebo is 2.2. So this line now corresponds with that 2.2. So of course, some value are more than the mean, some are below the mean. You expect it to be like that. Some value are below the mean. But if you look at the one that are below the mean, they are minus. The difference is minus. The one that are above the difference is plus. If you add them together, it gives you 0. That's why the only thing that makes sense if you want to analyze is to square them. Now you come to the second group, which is the low dose. The mean is 3.2. Can you see the line? Represent 3.2. While 2 are above, 3 that are below also. In the high dose, the mean is 5. Look at this line, it's 5. And 2 are above, 1 coincides with the value, 2 are below. Now, what I want you to see, you will see something like B1 and B2. It's looking at the difference between the two mean. So if you look at the difference between mean of placebo and low dose is the B1. If you remember the other time, the difference is this one is 2.2, this one is 3.2, the difference is 1. This different B1 is 1. The low dose is 1. Then the B2 is looking at the difference between this placebo and high dose. The difference, can you see, if you remember, the difference is 2.8 because the placebo, the mean is 2.2, the high dose is 5. So this distance is 2.8. Now, yes, you may be saying, why can't you have the one that shows the difference between the low dose and the high dose? Now, whenever the logic for this thing is just to prove that ANOVA and regression is the same thing. Now, whenever you want to analyze it like that, you have to use one as a reference. So here, libido is the reference value, which you compare the other two with. And that is why we are trying to look at the difference between I say libido, the placebo rather, is the reference one. So we want to look at the difference between the placebo and the low dose, which is the P1. And then the difference between the placebo, which is the reference, and the high dose. So if you look at, since you have 3 groups now, that dummy, if you want to do a regression, you have to create 2 dummies. These are the things that represent the 2 dummies. Because the first one, once you use one as a reference, we use the placebo as a reference. So you are trying to see how many times the low dose is higher than placebo, is different from placebo. Then how many times is high dose is different from placebo. So B1, B2, those are the regression, serve as a regression profile. And you see it in the values we have here. You see the value. 1 is the difference between the low dose and placebo. 2.8 is the difference between the high dose and placebo. But if you want to consider the difference between low dose and high dose, is there also, is 1.8. So I think we'll stop here. If you run it, maybe in the next, by the time we talk about regression, we will demonstrate the same data set you see. We run it with ANOVA, I run it with regression, it gives you the same thing. So interesting. And that is why when you run regression, there's a section of the result that is ANOVA, to analyze the variance. So I think we'll stop here. This is just to explain the post-hoc test. And we are through with ANOVA, but it's not just that we are through. We see have other, we have other sessions that talk about factorial ANOVA and other advanced this. I wouldn't know where, maybe the next lecture to proceed to explain those things or to move to other things, because to me, it takes somebody that is interested to want to know it. Though we have run all of them in our workshop, they are there. If anybody is interested, you can go and watch, subscribe and watch the video, the sessions where we do the workshop, we run all of them. Because if you don't do it, we don't run it, we don't have the practical session. The implication of it is that it's becoming more advanced and advanced. We are just talking to the ear. People don't just capture much. It looks more abstract. But if it is something that is workshop, you demonstrate, we run it. You demonstrate, we run it. Make it more interesting for people to grasp. So I don't know if there's any question. Any question? Today, many people are not many. We are just, how many of us here? 6 of us. Yeah. Any question? Yes, you have to unmute yourself if you want to talk, because many people, they are talking, you cannot hear because they are muted. You have to unmute your microphone if you want to talk for us to hear.
Yes, thank you, Dr. Lapo.
Okay.
Actually, I've missed a lot of these lessons because of time, not having time. But I think what I'll do is to subscribe to your is it what's it called, website, so that I can go over the
notes. You can get it there. All of them are there, and even the practical session where we run, we have the data set we go through. We first of all go to the logic, the science behind it, and we load it into SPSS and run it, and we look at the results. So interesting. So it's there.
Okay. So thank you very much.
You're welcome, sir. Okay, Professor Wakwe said you cannot hear. Can you hear now? Professor Wakwe? Okay. Maybe it's network. Any other question? So if there's no question, I think want to everyone.
Hey, just a quick one.
Okay.
Just thinking back. You talk about those conditions that has to be true. Do one have to? I believe one has to test for those conditions before running the post-hoc test.
No, post-hoc test. Okay, yes,
Yes.
So for you to know which one to choose. Yes.
Yes.
Yeah, you're right. Yes.
To be able to at least to be sure that the variants are the same, you know.
It's normally distributed.
Yeah, there's normal distribution, you know. Of course, maybe by the time you do you just run the data set, you're able to see whether it's normal.
Yeah. Yes, so, we try to explore. When you explore the data, you go to exploration, where it shows you want to plot the normal, you want to plot the histogram, stem and leaf. We do it, just plot. We just go, if you go to SPSS now, just under descriptive, you see explore. When you click on explore, the dependent variable, you put the if it is age or if it is libido, you put it there. You now say under it, you see that you want you to click. You want by default stem and leaf will show, but histogram is not. But you click on it because stem and leaf give more information than histogram. They are doing the same thing. So by default, the stem and leaf is click. Then you can click histogram if you want to. Then you want to normative plot with test. So the normative plot, the test there is Kolmogorov-Smirnov test or Shapiro-Wilk. There are two of them. If you click on that normative plot with test, it will go around Kolmogorov-Smirnov and Shapiro-Wilk to show you if it's significant. What the logic behind is that in the software, there is a data set that has been put in the software that follow normal distribution, perfectly follow normal distribution. So your own, it will now compare that data set inside that computer with your own. If your own is normally distributed, even if it's not perfect, normally there won't be any significant difference between the one inside the computer and your own. The both of them are equally normally distributed. But if there is your own is skewed, it's not normally distributed, they will be different. So the way to interpret is that if the p-value is less than 0.05, that shows that it's not normally distributed, it's skewed. But if there's no difference, the p-value is high, that shows that your own normal data set is not significantly different from the normally distributed data set that we programmed into the computer. I don't know if you understand. That's the logic behind the test. Those Komograph, Smirnov, and Shapiro-Wilk tests. So that is how to do that. Now, if let's say now is too, even in ANOVA, if you want to actually know if the variants are different, you know. Sorry, the network knocked me out. So if you are dealing with two groups now, if you want to go and you can even go and make effort to carry out t-tests. In carry out t-test, one of the output in SPSS is 11 tests for 11 tests for homogeneity, for equality of variance. So even the t-test give you two options, just like the one this one give. It will give you one for equality of variance, one for when variance are not equal. It give you, so you can actually see if there's homogeneity of it. But there's something about all this. If you are dealing with, if t-tests are over, they are regarded as robust tests. A robust test is a test that is still valid when not all the requirements for using parametric tests are met. Look at, for example, this example of libido we are using. Professor Wakwe once raised an issue here when we're running it in the workshop. He said that the libido score, when that score is probably on the scale of 1 to 10, you know, they just, it's subjective. They just after somebody you have taken a certain score on a scale of 1 to 10, how will you say when your libido is highest is 10? If it is lowest, maybe it's 1. So they not say, where will you put your libido now? You will just put some. So if you look at it, it's a rank scale on its own. So that type of data set, with the fact that it's even this, the sample size is very small. We are talking of 5, 5, 5, 10, 15 of them, 5 in each group. Because you cannot, even something that is normally distributed, normally, when you sample size is very small, that data set will not be normally distributed. Because any data set that is less than 30, when the degree of freedom is less than 29, you are not likely, it may not likely follow normal distribution. Those are the issues. But we still use them because ANOVA and t-test, they are robust tests. They are still valid. We still use them. They are still valid. Especially when even sometimes something that is put on a Likert scale, something 1 to 5, 1 to 1, agree, disagree, strongly disagree, disagree, neutral, agree, agree, and strongly agree on the scale of 1 to 5. And if the sample size is very large, you can still use t-test. And because if you use parametric and number, you see that there's no difference in the output. Doesn't differ. So those are the issues, you know, that come into play. And sometimes also when you are dealing with those ranks scale, you know, sometimes when you are not summarizing it, you may say, okay, this instrument has 20 questions, and the question they are grouped into 4. This one, number 5 of them is looking at the personality. One of them is looking at the psychological aspect. You know, the same, different things like that. By the time you are, how do you calculate the composite when you merge all the 5 and divide? Sometimes you calculate the average. By the time you calculate the average, you have introduced decimal. When you introduce decimal, something that is either 1, 2, 3, 4, 5. By the time you calculate average, you give it 3 point something, 4 point something. You can treat it. Once it becomes a continuous scale. Once it becomes continuous, you can use a parametric test to do it. Those are the issues. So all those things, you know, a lot of argument on the once you understand what you are doing. Yes, first of all, if you look at it, you remember when we run the Hoc test, it also gives us those one when equal variance assumed is equal variance not assumed. It's not process. Sorry, when we do plan, is it plan contrast? Something like that. Yeah, plan contrast. Yes. In plan contrast, it gives us one equal variance assume, equal variance not assume. Sometimes also you can actually know if the equal variance will be there, because by the time you look at their standard deviation, even by looking at it, that they are significantly different. One is, the standard deviation is bigger in one, while the one is smaller. You know that there won't be homogeneity of variance in this situation. Then another thing, when the sample size there is not the same. When you are having maybe, sometimes if you are doing your study, maybe comparative study, you may say 200, 200. That one is understandable. But there are some study, maybe all of them are 400. You now say you want to look at the difference between male and female. And whereas the male and female there, they are not 200, 200. So you see that maybe out of the 400, we have 350 female, and you are now having out of 500 you have 350, or 400 you have 250 female, 150 male. It's not the same number. They cannot have the same variance, because the variability reduces, or the precision increases when the sample size is high. So the one that has lower sample size will have higher variability. The one that have higher sample size will have lower variability. It's more precise. So you see that when the samples are not the same, there's no way they will even have the same variability. There will be normally homogeneity of variance. So when you are dealing with something like that, you want to test, sometimes you say, compare between the different marital status. When most of them are married, only a few are widow, all those stuff. You see, you have 3 group or 4 group, but it's seated to one side. It may be inappropriate for you to use ANOVA. You may have to use non-parametric counterpart, which is Kukawali, because for the fact that it's not the same number in each group, there's no way you can have equal variance. It's not possible. Those are the things, even from, without even doing any test, you know if equal variance is assumed, equal variance not assumed. I think we'll stop here, and if there's no other question, is there another question?